Welcome to your lesson on simplifying radical expressions. Let's get some vocabulary out of the way first so you understand the difference between the word root, radical, and surd, because maybe when you've seen this sign, you've actually heard all three words used to express what this is. So let's clarify a couple things. First of all, that sign itself is called a radical sign. So when you see radical, it means that sign. It means only that sign. That is the radical. Uh, Sometimes also it's called a square root, though, because it's going to be taking a square root of some number. So inside here, you could have some number that you want to know the square root of. When we don't see any number right here, we assume it's a 2. It can also be called a cube root. So when you do see a number there, let's see a 3, it means a cube root. It can also be higher ones like square root of 4, square root of, fourth root, fifth root, sixth root, and so on. So here's an example of a square root, root of 25. Square root of 25 is 5. Of course, you know that. Again, think about why that 2 is that we don't see is actually there. There's a 2 there. It means what number times itself twice makes 25. Cube root, as a difference to that, is we see a 3 there. So now we're thinking what number times itself 3 times is going to make 8. So 2 times 2 times 2 will make 8. All right, so if that's a radical, it's just a sign. Let's talk about what a surd is. A surd is an irrational number written using the square root sign rather than a decimal. So here's an example of a surd. We know this is irrational. This is not a perfect square root, like root of 4 would make 2 or root of 9 would make 3, but this one is irrational. So if you actually calculated that, you would get a decimal that goes forever and never repeats. And that kind of decimal obviously is impossible to write because it goes forever. So we keep irrational roots in this form, and this form is called a surd. All right. So of these three, which one is a surd? Well, 11 is a surd because it's an irrational root. This one obviously is not. There's not even a radical sign there. This one, we know a square root of 9 is 3, so it's not a surd. How about of these three, which is a surd? Well, root of 18 is a surd because we don't have a perfect square for that. Root of 81 makes 9, so not a surd, and root of 24 is, because we can't take that square root either. Great, let's look at perfect squares. As you know, here's a multiplication table. 1 times 1 is 1, 1 times 2 is 2, and so on. 8 times 10 is 80, all right? Hopefully you know your multiplication all the way through 16. So 16 times 16 is 256. So in yellow, in the middle, we have the perfect squares, because 1 times 1 is a perfect square. 2 times 2, 3 times 3, 4 times 4, 16, and so on. These are perfect squares, right? These are the numbers we can take the square root of. All the other ones, if you try to take a square root, will be irrational or a surd. So where does the word perfect square comes from? Where does it come from? Well, obviously, 2 by 2 makes a 2 by 2 square, and 4 is a perfect square because 4 is a perfect square. The sides are 2 by 2. Likewise, 9 is a perfect square because it comes from a 3 by 3 square, and 25 is a perfect square because it's made by multiplying 5 by 5, which is a perfect square, right? So those are perfect squares. There's a 225 is also a perfect square because 15 times 15 makes 225. That number is your square. This is called the root, right? So we can actually rewrite this in this form. The two 15s can change to square root of 25 because square root of 25 is 15. So that times that, root of 25 times root of 25 can actually make 225. All right, so there we have it. Let's go on. We're going to take some notes now. So from now on, grab your notebook and examples and notes that we are presented with, please add to your notebook. First of all, this title, Square Root, Radical Rules. We're going to begin with some basic rules today and move on to some more rules next time. So first of all, when you take this square root of something squared, it is just that number itself. So that root sign and that square actually kind of cancel each other out. An example is the square root of 5 squared is actually 5 because the root and the square cancel each other. Why does that happen? Because 5 squared is 25 and the root of 25 is 5. So there it is. Here we have square root of x outside of parentheses square. In that case, it's the same as this. Here we have a root, a square root, and a square inside. Here we have a square root and a square outside. they cancel each other the same way. It doesn't matter where that square is. It can be inside or outside the root. Either way, they cancel out, and we're left with just that number. For example, we have our root of 7 squared. That 2 and that root cancel, and we're just left with 7. These are basics of radicals. We're going to use them in the work we do today. So what is that going to equal? Well, another way to think of this, I just said that you can cancel those, but another way to think of it is that you have a root of 10 and times another root of 10 because you have 2 of those. And that makes a root of 100. That's how roots work. These things actually can become one root. And a root of 100 is 10. So this is going to be 10. Squaring, it just cancels out the square root side. We've already established that rule. Let's take a look. Try this one. Well, hopefully you got 15. Next one. A little bit more going on here. Think carefully about this one. Well, that one's going to be 9 times 7, or 63. Why? Because that square has to apply to a 3, which makes 3 squared, which is 9. And it also applies to this root of 7. And as we know, those root and that square will cancel, so we just have 7. That's 63. Try this one. Well, that one is 25 times 6, because again, that square goes on at 5, 25, and that square cancels out that root, makes 6. So we have 25 times 6, which is 150. All right, let's see simplifying radical expressions where it is not a perfect square. So the root of 18 is irrational. We don't want to write that decimal, that goes forever, but we can simplify this. It's important to know simplification. We look at this 18 and we see if there's a perfect square. Can you think of a perfect square that 18 can be composed of? Well, yeah, 9 times 2. 9 is a perfect square, and 9 times 2 makes 18. So we rewrite this like this. And now we can actually look at these two things, and if we can take the square root of one of them, we do. So we can take the square root of 9, which is 3. So there's that 3, we've taken the square root of 9. But the root of 2, we can't take the square root of that. We leave that as a root 2. So that has been simplified into 3 root 2. Simple process, but if you have trouble thinking in your mind of perfect squares and multiplication tables, this will be tougher for you. So try this one. All right, well, let's take a look. There's another process, another way to do this. It's called using a factoring tree. First of all, if you are good at thinking multiplication, this one, 50, is actually 25 times 2. 25 is our perfect square, so that becomes 5 root 2, because we take the square root of 25, we get 5, and the root 2 remains there. But using a factoring tree, 50, if you remember factoring trees, you can go like this and break it into two things that make 50. Maybe you were thinking of 2 times 25. That would have been fine as well. But 5 times 10 makes 50. 5 cannot be broken down any further. It's a prime number. But 10 can. 10 can be broken down into 2 times 5. So now we know that 5 times 2 times 5 makes 50. So we can rewrite our root as those three things, right? 3 things at the end of the factoring tree. 5 times 5 times 2. And anytime you have a pair like this under a root sign, it just comes out like that. And the reason again is because those will make 25. And just like here, the root of 25 makes 5. And that's what we have here. The root of 25 makes 5. So maybe you'll choose to use factoring tree, maybe not. It's your choice. Maybe this is easier for you to come up with that right away. So try this one. Well, that one, 120 can be broken into 4 times 30. 4 is a perfect square, and the square root of 4 is 2. So the 30 remains in there, the 2 comes out because we can take the square root of 4. 30 doesn't break down any further into perfect squares. Like 6 times 5 makes 30, or 2 times 15, or 3 times 10, but none of those are perfect squares. So we leave that as it is. Try this one. Oh, sorry, using a factoring tree, that would look like this. 120 is 10 times 12. 10 breaks down into 2 times 5. 12 breaks into 3 times 4. 4 we can take further into 2 times 2. So these are the final numbers at the end of the factoring tree. They're the prime numbers. So root of 120 can be rewritten as all those numbers multiplied. 2 times 2 times 2 times 3 times 5. Again, anytime you see a pair of numbers, we can remove that from under the root. So 2 times 2, we take that 2 out, and 2 times 3 times 5 remains under the root. 2 times 3 is 6, times 5 is 30, so there's a 30. So again, from that pair, 2 came out, the rest of them remained under there. And it's the same answer as here. All right, try these two. First one, 125 is 5 times 25. That's the perfect square right there. So we can think of it as two parts, and the root of 25 is 5. So this 5 comes out, that 5 remains under there. We have 5 root 5. Try the next one, root of 98. Hopefully you thought of a perfect square that makes 98. It's 49. 2 times 49, then you take the square root of 49, which is 7. So that square root, 7, 2 remains under there. There it is. What happens when you have numbers outside the radical? So let's look at this. There's a 7 there. Well, you can still do the inside as before. So 24, two numbers that make 24. Well, 4 times 6 makes 24. And the square root of 4 is 2. So that square root of 4, that 2 comes out here. And you see the 2 is here now. And you have 7 times 2 on the outside. Root of 6 remains inside. And 7 times 2 is 14. So now the outside is 14 because we had that 7 out there already. Root 6 remains. This one here, 108. Well, 108 is made of 36 times 3. You're always trying to think of the perfect squares, right? If you keep the perfect squares in your mind, like 4, 9, 16, 25, 49, sorry, 36 as well. Keep those in your mind, and then the number you see, always think, can I break it down into one of those? So 36 times 3, the square root of 36 is 6. So a 6 jumps out right here. That 6 comes out. We have a 4 times 6 on the outside. Root of 3 remains in here. 4 times 6 is 24. There you have it. All right, try these two. Try this one first. All right, hopefully you automatically in your mind, I hope 9 times 10 came to you, and 9 is a perfect square. So we can take a square root of 9. So square root of 9 is 3, so 3 jumps out of the root, 10 remains. 6 times 3 on the outside is 18, and the 10 is there. Try this one. Well, 80 is 16 times 5. There's our perfect square right there. Take the square root of 16. It's 4, so the 4 is there now. Negative 7 times 4. Root of 5 remains. Negative 7 times 4 is negative 28. And root 5. There's our answer. All right, it's practice for the skills key, especially if you don't have much experience with it. There's a homework page with practice problems of this type in the lesson. Please do that now, do your best, and you can check answers. There's some answers provided to the first page. You can do it.